Hi, guys. Today we're on Unit 11, Lesson 6, and we're going to be talking about some more derivative applications that we can do now that we know how to use the derivative, how to find a derivative using an easier method. So there are many different types of problems that can be solved using calculus. Yesterday, we used the derivative to help us write the equation of a tangent line. Today, we're going to talk about some basic problems involving geometry and physics. Okay, so let's just start with some basic notes here. Okay, we know when we want to find the average rate of change on a given interval of a function, okay, we've referred to that as the slope of a secant line, which is f of b minus f of a over b minus a. I kind of revert back to that when I'm setting up my average rate of change. And then we also know we can find the instantaneous rate of change. And the instantaneous rate of change we call the slope of the tangent line. Now we could go back and rewrite it as the limit, but why bother? We know that we can find the slope of the tangent line by using the derivative f prime of x. Okay. So different types of problems. You have to know when you have to find f prime of x and then plug in the x value. And that's going to give us the instantaneous rate of change at a specific time. Or we can set f prime of x equal to 0, solve for x. And that's going to give us where we have our maximum or minimum values, right? That's going to give us turning points on the curve. So those are the basic things. And then when we start to talk about our physics problems, our physics types of problem, okay, we're just going to kind of deal with problems that involve the position of an object. I know there's more to physics, but we're going to deal with the position of an object. And when we do that, we're always going to start with a position function. And more often than not, it will be given to you as s of t or h of t. And these functions relate distance and time. And we'll talk about that more in just a moment. When we want to find the average rate of change, we're going to use s of t and set up the slope of the secant. When we want to find instantaneous rate of change, I should have just wrote it. That's okay. We're going to use the derivative s prime of t. And when we use the derivative, right, when we relate this, the change in position over the change in time is going to give us our velocity. So the derivative of position is velocity, or how fast something is going. And again, I'm going to go into more detail with that, okay, when we get to those types of problems. Let's start with something simple here. The volume V of a right circular cylinder of height 3 feet and radius r feet is V equals, so we're going to get volume by plugging in radius. V of r equals 3 pi r squared. Find the average rate of change of volume with respect to the radius from r equals 3 to r equals 3.5. Okay. Most important thing here, okay, now we're dealing with, I have a cylinder. Usually I put the picture in there for you, and it doesn't even really matter. But the volume of this cylinder is given by this formula, right? The key word here is when you set up the average rate of change, you want to know, use the original function. Average rate of change is the original function, and you're setting up the secant line. So we're going to do V of 3.5 minus V of 3 over 3.5 minus 3. And you're just going to plug into your volume formula. So I have 3 pi times 3.5 squared minus 3 pi times 3 squared over 0.5. I'm not even going to worry about the pi's. I'm going to leave it in terms of pi. We wind up getting 36.75 pi minus 27 pi over 0.5. Subtract those two numbers. What do I have here? 36.75 minus 27, 9.75 pi over 0.5. I am going to take and I'm going to do 9.75 divided by 0.5. I'm going to work on the number part, leave it in terms of pi, it's fine, equals 19.5 pi. Now, when we do these types of problems, in calculus, it's going to say indicate units of measure. So we want to think about describing what's changing. If you think about this, we're talking about the change in volume over the change in time. Okay. That's what our slope was, the change in volume over the change in time. Our volume is feet cubed, and our time is given in feet. Sorry, it wasn't over the change in time. That's what's screwing me up. That's when we get to physics. It's the change in volume with respect to the radius. So it's the change in radius, and that's measured in feet. Don't simplify this. Okay. You're describing how it's changing. It's changing as feet cubed per foot. So our units of measure on this would be feet cubed per foot. And leave it, it's fine. Now we want to find the instantaneous rate of change with respect to the radius. Instantaneous, you're going to use the derivative. So I start with my original function, and I'm going to find the derivative of that function. So V prime of R is going to equal 6 pi R. And now if I want to find it at the instance the radius is 3, I'm going to plug in 3. So V prime of 3 equals 18 pi. And again, my units of measure are going to be feet cubed per foot. So this problem just basically showed us the difference between when we want to set up a slope of a secant line, average rate of change, use the original function and set up that secant line. Instantaneous rate of change, use the derivative and plug in the specific value. Okay. It's a very basic geometry style problem. Now let's look at a more physics type of problem. The position of an object, S, at any time t is given by S of t equals negative 16t squared plus 128t plus 100. S is measured in feet, t is measured in seconds. Before we begin, let's visualize, let's think of what this picture looks like. Not gonna, you can put it in your calculator if you want to, but you should be able to see this. It's an upside down parabola. So I have an upside down parabola. My y-intercept is 100. And it goes something like that. That's all. So the position of an object when t equals 0, right? This is my time. And this is my position, or s of t. It's at 100 feet. It goes up, 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 reaches its maximum point, and then starts to go down and hits the ground. Okay, so that's hitting the ground. Find the average speed of the ball between t equals 0 and t equals 3. So we want the average speed of the ball between 0 and 3. 3 is probably going to be about here. We're looking for the slope of that secant line. Average speed, use the original function and set up a secant line. S of 3 minus S of 0 over 3 minus 0. So it's your job to know how to find these values. We're going to plug 3 into the original, 0 into the original. You could do it in your calculator. We might as well put it in our calculator. Negative 16x squared plus 128x plus 100. If I'm working from the graph, I can just do second trace 3, and I get 340. When I plug 0 in, I see I'm going to get 100. So I have 240 over 3, or the slope of that line is 80. The average rate of change. Now think about this. Okay, what's my units of measure going to be, right? I have 80. My height, my position, my change in position over change in time. My position is measured in feet. My time is measured in seconds. Okay, so this is 80 feet per second. The average rate of change, also it gives you how fast it's going. It's just the average. Now we want to find the instantaneous speed of the ball. Okay. Speed is basically the same thing as velocity. However, if it said velocity in the problem, you'd use whatever sign you get for the answer. When it's speed, you're just going to take the absolute value. Okay. And I'm not going to go into too much detail there. Just know that velocity, okay, use whatever sign you get. And speed, no matter if you're going positive or negative, you're always going to give positive as your answer. Find the instantaneous speed of the ball at time t. Instantaneous speed of the ball means that you're going to take this original function and if you want to find the speed of the ball at any given time t, we're going to use the derivative. And remember, this is what we call a velocity function. So now you can represent it with S prime of t, or you can use V of t, whatever you want to do, but you have to know that once you find the derivative, you now have a function to give you how fast it's traveling at a specific value. Find V of 0, or in other words, the initial velocity, right? So basically this question is how fast is it changing, or how fast is position changing? At t equals 0, right? That's another way to ask that question. So I'm going to plug 0 into my velocity function. V of 0 is 128 feet per second. Let's go over to our graph for just a moment. what we just calculated was the slope of that line. That line represents how fast it's going. The slope of that line represents how fast it's going at that particular time. Okay. And again, our velocity from our formula is positive because it's moving in the upward direction. So it's traveling 128 feet in the upward direction. Find the velocity at 3 seconds. Means plug 3 into your velocity function. What I wind up getting there. I got 32 feet per second. If you evaluate that, you're going to get 32. Again, velocity is measured in feet per second. Let's find V of 5. It's not on there, but let's find it. V of 5 would be negative 32 times 5 plus 128. And I get negative 32 feet per second. Let's go back up to our picture. When t is 3, the slope of that line is 32. So that slope represents how fast it's going, right? When t is 5, I get negative 32. My slope is negative 32 feet per second. This just means it's moving up, and this means it's moving down. That's all. So if the question has velocity, leave your sign in your answer. When is the velocity of the ball equal to 0? Okay. So the velocity is going to equal 0 when we set the derivative equal to 0. Right? And that's going to be here, right? The velocity is going to equal 0 when the slope of the tangent line is 0 or horizontal. Right? So we're going to find that by setting what we got for our velocity function, the derivative of position. And we're going to take that function, negative 32t plus 128, set that equal to 0. Negative 128 divided by 32. The velocity is going to equal 0 at 4 seconds. How high is the ball? How high is position? So if we want to see how high the ball is when the velocity is equal to 0, we're going to plug 4 into the position function. Because the S function gives us position. So S of 4, I'll write it out for you, even though we're just going to plug it into the calculator. And you can go into your calculator, second trace, plug in 4. What's the Y value on the function, or what's the highest point on that graph? How high is it? It's 356 feet. Let's add on a part here. What is this, part G? Let's add on. How fast is the ball going when it hits the ground? In other words, what is the velocity of the ball when it hits the ground? So we need to do what? We need to find out when it hits the ground. Look at your picture. When does this ball hit the ground? Well, this is the ground over here, but that doesn't matter. It hits the ground at this root. So we need to find that value. Okay. I'm not sure. I don't think we're going to be able to factor this one. Okay. So we're just going to go straight to our calculator. I want to remind you how to find a zero. So we're going to second trace 0. And we want to move closer to the 0. So we just got to move our cursor down. I can find it. I went way back past it. There we go. Enter. I'm going to get a right bound. Enter. And it hits the ground at 8.71699 seconds. So let's just, for the sake of things here, just use 8.7. So it hits the ground at t equals 8.7 seconds. We want to know the slope of the tangent line. We want to know how fast it's going. So we're going to plug 8.7 into our velocity function because that gives us how fast something is going. Negative 32 times 8.7 plus 128. And if you do the math for that, you would get negative 150.4 feet per second. So basically, moving up to our picture really quickly, when that ball hits the ground, it's traveling in the downward direction, negative 150.4 feet per second. Okay. There's a lot of stuff going on here, guys. When you do these problems, you have to read them carefully. When you're dealing with an average rate of change, you're setting up a secant line, you'll be given 2 x values, use the original function. Anytime you want an instantaneous rate of change, you're going to plug a number into the derivative or set the derivative equal to 0 and solve for x. Okay, so you really have to be careful to read your problem and practice, practice, practice. So you have a homework assignment for tonight. Please do it. And I'll see you tomorrow. Thanks, guys.